the direction of motion, right? Whether it was going up or down. And in that case, we saw in that problem, it could have went up or down depending on what the load is. Can everybody picture the problem? Go back in your notes to the problem. There was a block and there was a load P, and if P was huge, if P was big, it was going to slide up. And if P was small, it was going to slide down. So we had to do the analysis for two ways. Everybody has that, right? Everybody with me? Okay, so now, that friction equation, the frictional force is equal to mu n. When could you use it? Can I use it right now, even though I'm not moving? No, I can't use it now, right? But as soon as impending motion is about to occur, when we have starting impending motion, that's when you can use it. The frictional force is equal to mu n when motion is about to occur. And on that problem we did, you knew that they were talking about impending motion. Either it was going to slide up or it was going to slide down. So we analyzed it for it sliding up, we analyzed it for sliding down, and we found a range of P where it would be in static equilibrium. Excuse me, the reason why I'm talking about impending motion now is because that's what we're looking at in this type of problem. So let's read it first. A force of 500 newtons, okay, they're showing us. It's applied at the end of the cord that's attached to block A. Block A weighs 2,000 newtons, and block B weighs 4,000 newtons. The coefficient of friction between the blocks is 0.3. The coefficient of friction between the block and the floor is 0.2. And then let's ignore A and B for now. Okay? So let's see, how do we start out the problem? Oh, another thing in the test, about more than 5 of you, less than 10 of you asked me what the setup meant, the word setup. You guys know what setup is. What is setup? Given, find, table, number of unknowns, so number of equations, number of bodies, right? Then draw your free body diagram. That's all the setup, right? You know that already, okay? That's what setup is. I don't mind answering questions. I'm glad you asked when you're confused, but you do know it. I think sometimes you just get stressed out on an exam, and then you're like, oh my God, setup, what's setup? What does she want to see? But you know it. Take a breath. You already know what setup is. Okay? When we did setup, before we did the equilibrium equations, what did we do? Between drawing the free body diagram and setting up the equilibrium equations, do you remember what that step was in between? Take a look in your notes for setup. Given, find, table, number of unknowns, equations, number of bodies, draw the body, then components. Remember, we solved for the components of forces. And why did we solve for the components before we started doing the equations? Because we could check. If we solve for the x, y, and z component of a force, and then we check it and it doesn't work out, we know we blew it already, and we could go back and check, and we could go back and correct it. And a lot of you didn't do that, which is fine. I'm not taking a point off, but that's another opportunity for doing a check, right? Find the components. You could check the unit vector. You could check the components before you move on to the equations. Okay? Okay. So, setup. Given. What information here is given that we didn't know from the drawing? The weight of A, weight of B, what is it? 2,000 newtons? 4,000 newtons. What else is given that's not, we didn't know? Mu between A and B is 3, and mu and, let's just call it B, is on the bottom is what? 0.2, right? Okay, and what do they want us to find? So let's just read A. If the system would be in equilibrium, if P equals whatever, B, the maximum force P for which the system is in equilibrium. So what do you really need to find? P. Just find P. So take a look at A for a minute. It says determine the system, determine if the system would be in equilibrium for P is equal to 20, is everybody listening to me? If P would be equal to 2,500. So, is the problem saying that P is 2,500? No, they're saying it may be or may not be, right? So, if you plug in 2,500 for P, if you say P is 2,500, your equilibrium equations aren't going to work, right? Well, I don't want to do that. I don't want to work with numbers that may or may not be correct. I'd much rather solve for P and then compare it to 2,500. Does that sound good for you guys? Find the unknown and then compare it. I don't want them to give me some bogus number and then it might not work. Okay, so we want to find P. So now we have our table. Our table, force, moment, magnitude, direction. And writing low on the board is making me think of this design that you guys are doing. Not only do you want to talk to the faculty that use it, you want to talk to the IT department. Because they're the ones who chose this design, and they might be investigating. Oh, yeah.
Do you have contact info with them?
Yes.
You do?
Okay. So you want to check with them, because they may be there on a different design, or why did they choose that design, or, they're not the user, but they're the ones who are in charge of IT.
Maintain the system.
Yeah. Okay, so what forces are in the system? Let's go around. Give me one.
Weight of B.
Okay, let's do both of them.
Okay.
The weight of A and the weight of B, because I'm running out of space. We know. Next, Chris.
The normal of B and normal of A.
Okay, so can I call it normal AB and normal B? Does everybody like the way I'm writing this? What does normal AB mean? The normal in between them and NB means the normal on the bottom. Do we know them? No. No. Direction? Yes. Oops. It's okay. What else? Armando.
Friction?
The friction force. So is there one of them or two of them?
Two.
Okay, tell me what you want to call them.
Friction AB.
Okay, and?
B. Friction B.
Okay. So you guys have to get up if you can't see. JJ. What other forces are present?
500.
500. Give me another one.
B.
And P. Anything else? Frictional forces, the normals, the weights. Okay, so how many unknowns? Brandon?
4 unknowns?
5, there's one more. It's hard to say. So there are 5 unknowns. So Brandon, how many equations do we need?
5.
And how many bodies do we need?
2.
2. Okay. But now let's go back to the problem. Eric, what are they asking us to find?
B.
B. How many unknowns is that?
1.
It's only one unknown. So from looking at, does everybody see this distinction? This is just the same kind of problems you've been doing. There are 5 unknowns total in here, which means we have to analyze 2 bodies. And Brandon, would you tell me why you picked 2 bodies?
Because there's 3 equations you can use.
Good, and tell me what they are.
Some of the moments, some of the forces, and some of
Okay, well let's
some of
back
the
up.
forces in X and some of the forces in Y.
Some of forces in X, some of forces in Y, and
Some of the moments.
can we do the moments? Take a
Oh,
look
the
at it.
friction equation.
It's the friction equation. Why can't we do moments? What's the giveaway?
No distance.
They didn't give us any distances, right? In real life, do we always know distances? We do. Usually we do. So then we could use the moment equation, and then we really have to decide whether we could use it or not. Okay, but in this case, they didn't give you distances, you can't use a moment equation. But Brandon, when can we use the friction equation? What did I say before?